Hello, so in this video I'm going to discuss another problem on real analysis. So the question says that let's say f is a function from R to R which is differentiable such that its derivative is never 0. Show that f of R is an open interval in R. So let's see the solution. So given that f is differentiable function and its derivative is never 0, so which means that its derivative f dash of x is either greater than 0 or less than 0 for all x belong to R, which means that f is monotonic. So if it is greater than 0, if f dash of x is greater than 0, that means f is increasing, and if f dash of x is less than 0, that means f dash is decreasing, and it is strictly increasing or strictly decreasing, hence it is monotonic. Now we know one result, that image of any interval under continuous map is interval. So I am not proving this, which is but I'll give you some hint. This is due to intermediate value theorem, which I left as an exercise. You can try this, and I'll use this result here. The result is image of any interval under continuous map is interval. Now what can you say about f of R? Now we know that R is interval, which is open minus infinity to open infinity. So f of R will be an interval, let's say I. Now as of now we prove that f of R is interval. Now we have to prove that the interval is an open interval. So to prove that I is an open interval, we have to prove that every point in I is an interior point. So we will prove it using contradiction. So let's say f of R is not interval, that is I is not an open interval. If it is not an open interval, then f of R can be of these forms: closed A comma open B, closed AB, open A, closed B, minus infinity to infinity, A to B, A to infinity, these kind of forms. But and also recall that f was injective function, it is monotonic function, and without loss of generality, let me assume that f is increasing. And also, and now I'll prove that f of R cannot be of any of this form, the form which I've given, the interval form which I've given here. Now, how will I prove that? Now let's say f is increasing and f of R equal to closed A comma open B. That means that f of R is obviously is greater than A. F of R is obviously greater than A. Implies that there exists some C naught belong to R such that f of C naught equal to A. Obviously, because f is attaining that point A. That means there will be some C belong to R such that f of C equal to A. Now what can you say about the image of C minus A? Now recall that since f was increasing, that means the value of C minus A will be less than A. But it is a contradiction, because we assume that f of R is greater than A. It's a contradiction. And now similarly we can show if the function is decreasing, and also by taking other forms of interval. So ultimately we got that if the function is increasing, then there cannot be any bound. There can be bound, but f cannot attain that bound. Here we are assuming that f attains the bound. Here minimum value is A, here minimum value and maximum value is A and B, there maximum value is B. So this kind of thing is not possible. Thus we proved that f of R is an open interval. Thank you.